Assalamu alaikum and good morning, everyone. Welcome to my lecture number 10 for CHM 577. And today I'm going to talk about crystalline state and solid state. And this lecture notes were originally prepared by Dr. Amalina, and I am presenting the notes for my students in my group. So, the expected outcomes of this lecture number 10 is for my students to be able to identify the types of metallic crystals, identify the types of ionic solid crystal lattice, calculate the net number of ions or particles in a crystal lattice, and calculate the age length and density in a cubic cell. And these calculations will actually allow you to predict based on the density of a particular solid to predict what would be the element that is in that solid. So as an introduction, solids can be categorized as crystalline or amorphous, depending on how their particles are arranged. So on one hand, you have crystalline, on the other, you have amorphous. So a crystalline solid um, possesses rigid and long-range order. In a crystalline solid, the atoms, the molecules, or the ions, and these atoms, molecules, or ions, they are collectively referred to as particles. These particles occupy specific positions in the solid. And the particles in crystalline solid, they are arranged in distinct three criteria. They have a regular pattern, they have a repeating pattern and three-dimensional pattern. So when you have particles arranged in a regular manner, that is a repeating pattern, and three-dimensional, then very likely that kind of solid is a crystalline solid. So crystals have highly regular features and they are said to possess symmetry, or they are said to be symmetrical. And crystalline solids are formed when hot solutions of any maybe salt, they are allowed to cool slowly and left to stand for a period of time. So if you would wish to have a crystalline solid, slow cooling is desirable, and then you do not disturb the slow cooling. You just leave it be for a while, for a long time, so that the particles can take the time to arrange themselves in an orderly manner, in a particular repeating pattern, and in three-dimensional. So you are going to get crystalline solid in that way. Opposite to crystalline solid is what's called the amorphous solid. Now, amorphous solids, they do not possess a well-defined arrangement and they do not have long-range molecular order. The particles are scattered randomly. There is no pattern, there are no well-defined faces, angles, or shapes. The mixtures of molecules do not stack together very well, large, flexible, and these are typically formed, amorphous solids are typically formed when hot liquids are cooled very rapidly. So if you can imagine a hot molten sugar. Yeah, have you seen sugar being melted in a pan and very hot? And if you cool down that molten sugar very fast, very quickly, you are going to get a structure which has bubbles, very brittle and amorphous, no pattern, very, very random, as opposed to that crystals, the crystalline solid that I was telling you about. To obtain crystals, you have to allow slow cooling, undisturbed, and you're gonna get a very, very beautiful, shiny faces. Whereas usually, if you can imagine sugar, hot sugar being cooled down fast, is going to be very dull. No facets, no faces. It's just very amorphous. Okay. And there are four types of crystals now. You can have metallic crystals, you can have ionic crystals, simple molecule crystals, and macromolecule or giant molecule crystals. Now let's go through one by one what are the differences of these types of crystals. Now metallic crystals, the particles are obviously metal atoms. For example, sodium. No, sodium is not a good example because sodium is soft. Let's take chromium, for example. Chromium metal has very, very good um, crystalline structure. The particles are obviously metal atoms, and the bond that is found in metallic crystals are metallic bonds. And three common types of metallic crystal structures: you have body-centered cubic (BCC), you have face-centered cubic (FCC), and you have hexagonal close-packed, which is called HCP. So these three, which are BCC, FCC, HCP, they are common types of metallic crystals. Now, the next type of crystals that you may find in nature is quite common, which are called the ionic crystals. Of course, the particles that you find in the ionic crystals are anions, which are negatively charged ions, and cations. So the anions and cations exist as particles in ionic crystals. And obviously, you have ionic bonds that hold the anions and cations together. There are two common types of ionic crystal structures. They are called sodium chloride structure or rock salt and cesium chloride structure, CSCl. There is another, we're going to discuss the third type, which is the zinc blende structure later. Okay, the third type of crystals is called simple molecule crystals. And obviously the particles are simple molecules. Within the molecules, you find covalent bonds. Within the molecule, you find covalent bond. Remember my previous lecture? But in between the two molecules, you may be able to find van der Waals forces. Yeah. So the molecules are held together between two molecules by van der Waals forces, quite weak, whereas within the molecule you have the covalent forces. No, sorry, covalent bond. And there are three common examples of simple molecule crystals: iodine crystals, phosphorus crystals, and sulfur crystals, where iodine is I2, phosphorus is P4, whereas sulfur is S8. And the fourth type, the fourth type of crystal that you are going to be brought into this, not this, maybe not this particular lecture, the lecture after this, what's called the giant molecule structure or the macro molecule structure crystals. And the particles in macromolecule crystals are non-metal atoms. So if you can recall, in the metallic crystals, you have the particles as metals. If you have non-metals, then you call them obviously macromolecules. The forces that can be found in macromolecules are extended network of covalent bonds. Yeah, you're going to have covalent bonds coming from this end of the crystal to the other end of the crystal so far away. Yeah, and the common examples of macromolecules are allotropes of carbon. So who knows what are the allotropes of carbon? Course, you have your graphite and your diamond. What are allotropes? I'm going to go through that with you in the next lecture. You can have graphite, diamond, silicon, silica, and boron. Those are examples of macromolecular crystals. And when we talk about crystals, you will come across a few terms. The term of symmetry or repetition in a crystalline solid, they're called lattice. Lattice, yeah? So this whole thing that I am pointing to you, this big structure here, this is called a lattice, where the particles that make up the lattices are called the lattice points. So these are the lattice points on each corner of the unit cell. And the unit cell is the basic repeating structural unit of a crystalline solid. So you have this is the unit cell, quite a small basic. This looks like a not a cubic, but probably an orthorhombic unit cell. And when you put these cells, stack them up, remember crystals have patterns repeating in three-dimensional. So when these are repeated in a regular pattern, three-dimensional way, you are going to get a lattice, which you have lattice points, where the lattice points can be atoms, metals, or molecules, or ions. Yeah, so the particles are located on the lattice points. So we'll go through a few seven basic unit cells. The first one is called the simple cubic, and obviously simple cubic is when you have the length of A is equal to the length of B and it's equal to the length of C. And then the angle alpha, beta, and gamma, they are all the same. You have the alpha angle 90, beta angle 90, and gamma angle 90. So this is the simplest unit cells, which you call simple cubic, where A equals to B equals to C, alpha equals to beta, and equals to gamma, and equals to 90. Okay, so that is the simplest unit cell. Now, the second unit cell is called tetragonal. So basically, it's the same as the simple cubic, but one of the edges of your cube is longer than the other two. So in here you have A is A is equal to B, but these are not equal to C. So you're going to have a tetragonal in this way. It's like a long cube. It's like probably a shoebox, yeah? And then you're going to have the third one. This is a little bit more varied. You have orthorhombic, where orthorhombic is the edge length of A is not equal. A is not equal to B, and they are not equal to C. But the angles are still very much the same. Alpha, beta, and gamma are still 90. The same with your tetragonal. You have alpha, beta, gamma is still 90. Okay, right. That is when you are varying the length of the edges of your unit cells. But if you do not vary the length of the edge, but you vary the angle, the unit cell angles, A is still equal to B, still equal to C, yeah? A is still equal to B, still equal to C. However, you have your alpha, beta, and gamma, they're not equal to 90. This is what you get. You are going to get a rhombohedral. So you have simple cubic, tetragonal, orthorhombic, and then the fourth one is rhombohedral. And then for monoclinic is when you have your A is not equal to B, not equal to C. Alpha is equal to B, alpha is equal to beta, and they are 90, but your gamma is not equal to 90. So you're going to get this type of structure. And then the number 6 is called, this is called monoclinic. Monoclinic is of A, B, and C. They're not equal to one another, but two of the angles are the same 90, but the third angle is not 90. So that is a monoclinic. But when you have everything not the same, A is not equal to B, not equal to C, alpha not equal to beta, not equal to gamma, and they're not equal to 90, you're going to get a unit cell which is called triclinic. So this is a triclinic. And then the last one is called hexagonal. This is the shape of a hexagonal unit cell where A is equal to B, but it's not equal to C. Alpha is and beta, they are 90, but gamma is 120. So to get hexagonal shape, this is the angles and the bond edges, the edges of the unit cell that you require. So we have simple cubic, tetragonal, orthorhombic, rhombohedral, monoclinic, triclinic, and hexagonal. So those are 7 basic unit cells. So when you are stacking any one of these basic unit cells, you're stacking them up, yep, in a regular pattern like this, you get a whole lattice. The whole lattice is like the whole structure. And then you're going to get lattice points and so on and so forth. Now, there are three common types of cubic unit cells in a metallic crystal. So we are talking about metallic crystals. Now, we're not talking about ionic crystal, neither are we talking about simple molecular crystal or macromolecule. We're talking about metallic crystals. Now, in metallic crystal, we are going to limit our discussion into cubic unit cells. Yeah. So you have simple cubic, which is usually referred to as CC, simple cubic. And then this simple cubic is really very easy to draw. It's just A is equal to B is equal to C, yeah? A is equal to B equal to C, and alpha angle is equal to beta angle is equal to gamma angle, which is equal to 90. That's simple cubic. And you are putting one metal on each corner of your simple cubic. Only one metal atom, one on the top, 4 at the top, 4 at the bottom, so you get simple cubic unit cells. But when you have simple cubic unit cell and you are putting one more atom of metal in the middle, you call that body-centered cubic. Obviously, there is something in the body of the cube. So you put the one particle in the middle of that cube. So that is called BCC, body-centered cubic. But if you vary the situation, you do not put this particle right in the middle. You put one particle on each face of this cube. Can you tell me how many faces are in this simple cube? I hope you come up to the number 6 because we have 6 faces. So you are putting one uh, particle on the top face. You're putting another particle on the right face, one at the bottom face, one on the left face, and then one in the middle face and one at the back face. So you have 6 particles on the surfaces of the simple cubics, and you call that face-centered cubic. So it's really very simple. Nothing in the middle, nothing on the face, you say simple cubic. If you have one particle in the middle of the cube, you say body-centered cubic, BCC. And if you have particle on the faces of the cubes, you say it is a face-centered cubic, FCC. Now, FCC is the closest packed arrangement of the 3 units that I show you, this one here at the top. It's the closest pack. That means they are the most efficient arrangement of particles to make this face-centered cubic. A closed pack arrangement can lead to either cubic close pack or CCP or hexagonal close pack HCP, depending on the placement of the third layer particle. So let's slowly follow this lecture and get your space imagination. Follow my lecture. Okay, for close packing, remember in here, this simple cubic is not close packing. This body-centered cubic is not close packing, but face-centered cubic is close packing. Yeah. Now, some textbook will refer, even your notes that you download from Dr. Amalina will refer to it either closest packing or closet packing. I prefer to call it close packing. Close packing maksudnya rapat. Dia pack rapat-rapat, padat-padat, ya. Close packing. So you can, if you pack your particles close together, you can either have hexagonal arrangement or cubic arrangement. How is that possible? Now let me pull you through the first layer. If you arrange your metal atoms, for example, in this way, these look like billiard balls, yeah, billiard round, beautiful little balls. So you're arranging these atoms in this closed pack where each one of the curve will be filled in by one ball. So that's why it is called close packing. Very, very rapat, very, very close. Yeah. So this is your first layer. And you take one more of this and you place it on top of your first layer. Your second layer, if you place it where the um, nook is being placed with one ball, so you call that close packing. So this is the second layer where your atom, this one atom here, your metal atom, is cradled by three different atoms at the bottom. It is placed at the crevice, at the hole between the three atoms. So you're putting it there. So it is the closest packing. Now, up to that point, it is still okay. Now, let's have a look at how you place the third layer. Now, if you place the third layer in this way, yeah, in this way, you are actually going to repeat the position of the first layer. Yeah. Remember, if this is your third layer at the top, you are putting it right in the middle there. You are going to repeat the first layer. So practically first layer, if we call it A, second layer, if we call it B, third layer, you call it A again. So it's A, B, A, B, A, B. If you arrange your layers of close pack atoms in the AB, AB, AB situation, you're going to end up with a unit cell which is called HCP, hexagonal close packed. However, if your third layer, you arrange it in this way, yeah, see, can you see the difference between how the three green balls are arranged differently from this blue ball? So if you arrange it in layer A, layer B, and layer C, A, B, C, A, B, C, and A, B, C, you are going to get in the end cubic close packed situation or CCP. So let me show you that to you in an exploded view. Yeah, to get your hexagonal close pack, you are putting one layer A, the second layer not the same as your first layer, so you call it B, but the third layer is the same as your first layer, so you call it A. So it is A, B situation, and it's going to give you hexagonal close pack structure. You can imagine it is very, very close, mampat, rapat, yeah? So A, B, A, B. But if you have A, B for the second layer, C for the third layer, and only the fourth layer you're going to repeat A, so it's A, B, C. Can you see the difference between the orientation of the layer B and the layer C? Layer B is the corner of your triangle is facing me, whereas in layer C, the corner of your triangle is facing you, the other side, yeah, if we are in the classroom. So if you have ABC arrangement, you are going to get what is called the cubic close pack structure. Yeah, so that is the exploded view. So this is a repeat of what was said in the slide number 9. I don't think you have it in your original that you download from Dr. Amalina, but you can have this later. I'm going to give you later this slide. So AB situation gives you a hexagonal close pack, but ABC situation is going to give you a cubic close pack, and cubic close pack is sometimes called face-centered cubic. Yeah, that is your face. Can you see that it is face-centered cubic, FCC? Yep. So you are going to get that unit cell, this unit cell of face-centered cubic, the one that we are talking about here. Here, this is your face-centered cubic unit cell. Yep. And how you get the face-centered cubic unit cell is through the ABC arrangement of closed pack layers. Yeah. In here, you kind of get a body-centered, but it's not quite body-centered. It's actually hexagonal later. I'm going to show you later how it is becoming hexagonal. Okay, going back to the 3 types of simple cubic, body-centered cubic, and face-centered cubic, I'm going to show you how you are going to calculate the number of particles in one unit cell. Okay, this is a drawing of a simple cubic or SCC. If you look at it, all these atoms are made fatter in here, looking like that. You are going to see that each one of these particles at the corner of the um, cube, they do not all belong to that cube. In fact, if you cut this atoms that are fattened up like that, you are going to see this situation where each one of the corner atom actually only belonging 1/8 of this cube. Yeah, can you see that atom there that belongs to that particular cube is only 1/8, but there are 8 of them, so 1, 2, 3, and 4 at the top, and another 4 at bottom. So 1/8 of an atom times 8. So for simple cubic structure or unit cell, you are having 1 particle per unit cell. And you can see here that the coordination number of the one in the middle, or in fact, this one in the middle is actually exactly the same as the one on the side or at the corner if you extend the lattice. Yeah, if you extend the lattice. So we take this one in the middle, you are going to really easily see that each one of these will be connected to 6 other metal atoms. So one at the top, at the bottom, and then 4 corners of this. So the coordination number of each of these atoms in simple cubic is 6, and the number of atoms in one unit cell is 1. I hope that is clear to you through the calculation. And moving on to the next type of cubic unit cell is a body-centered cubic, BCC. The same, you still have 1/8 of the atom at the corner, but there is one big one in the middle. Remember, it's body centered. There is one big one. So it's 1/8 of an atom times 8 plus 1 in the middle. So for body centered cubic, you have 2 particles per unit cell. And let's see how that is different from your face-centered cubic. Face-centered is like this. Yep, this is the structure of face-centered cubic. Okay, I'm going back here. No, I'm going back. I'm going back here. I've not talked about the coordination number. So if you go back to your body-centered cubic, and you're going to see that each one of this particle is being touched or being attached to 8 other particles. So the coordination number of each one of this body-centered cubic is 8, unlike the simple cubic, which is 6. The coordination number is 6. But for body-centered cubic, it is 8. And comparing it with that face-centered cubic, you're going to see that the coordination number of this particular particle in the face-centered cubic, which is the same as any other the others in that situation, is 12, whereas the number of atoms is going to be counted slightly differently. So you're going to have 1/8 times 8. So there are 8 blue there. 1, 2, 3, 4, and then 4 more at the bottom. So 1/8 of an atom at the 8 corners, and half of an atom on 6 faces of your cube. Can you see that if you put an atom on the surface or on the face of a cube, it is being shared by 2 units, and half of this yellow belongs to the unit cell at the bottom, and another half belongs to the unit cell at the top or on the sides or at the back. Yeah. So half of the atom at 6 faces, so it is 1/8 times 8 plus half times 6. So you're going to get 4 particles per unit cell in FCC. So can you see the gradual density increase for the 3 units? In here you have, for simple cubic, per cube you only have 1 particle. But for your body-centered cubic, in each cube you have 2 particles. And going further down, for face-centered cubic, in 1 unit cell you have 4 particles. So you can see the density of these arrangements increasing as we go along, from the simple cubic to body-centered cubic to the face-centered cubic. This is another way of counting the net number of particles. This is a repeat. This is a repeat of what I have explained to you earlier. This is, you can see, an atom at the corner of a cube is shared by 8 unit cells. There you go. So 1/8. So you have 1 particle per unit cell for simple cubic. If you have a particle on the face of that cube, it is on the face of that cube is going to be shared by 2 units, so it's half. But if it sits on the edge, it is going to be shared by 4 unit cells on the edge. But you have not seen a situation so far that I described in this lecture about the edge. We'll go to it later. This is really, again, putting the same information together in one slide. So simple cubic, 1 particle per unit cell, body-centered cubic, and then the The coordination number is 6 for this one. Body-centered cubic coordination number is 8. Body-centered cubic coordination number is 8. Yeah, as you can see very easily, this one here is being touched by 8 atoms. Yeah, and the number of atoms, particles per unit cell is 2. And the number of particles per unit cell for face-centered cubic is 4. And then the coordination number is 12. This is another thing with an addition of hexagonal close pack. If you try to count, you already know body-centered, face-centered, hexagonal close pack. You're going to have 12 particles at the corner of your hexagon at the top. You're going to have 2 surface atoms, one at the top, one at the bottom. Yeah, the 12 is 6 at the top and 6 at the bottom, and then 3 center atoms. So if you want to count how many particles are there in hexagonal close pack, you are going to have 12 times 1 over 6, 2 times 1 over 2, and 3, you're going to get 6. 6 particles in one hexagonal close packed unit cell. Right, so that's really very simple. My lecture so far has covered the types of crystals and how you distinguish between simple cubic, body-centered cubic, face-centered cubic, how you count the number of particles in them, and what are the coordination numbers. And now this part of the lecture is to show you the relationship between the age length and the atomic radius, because it is really quite easy for you to determine the atomic radius of a particular metal atom if you are given the age length of that particular unit cell. For simple cubic, you can see very clearly here that the edge, which is A here, is actually double the radius of the atom, correct? Because this is one atom, the green atom, which is cut into 8, and each one of this is the radius of that atom. So for simple cubic, the radius of the atom is twice that of the length of the edge. So A is equal to 2R. That's very simple to understand. But when you come to BCC, body-centered cubic, you are going to apply some mathematics here. You are going to see from Pythagoras theorem that B squared, yeah, B squared, yeah, here is equal to A squared plus another A squared. Yeah, yeah, this is A squared. So C squared is equal to A squared plus B squared, and all this mathematical calculation, I'm no mathematics, I've learned this before, but for body-centered cubic, the age length is equal to the 4 times radius divided by square root of 3. And using the same kind of calculation for face-centered cubic, the age length A is equal to the square root of 8 of the radius. Yeah, square root of 8 times radius. So that is how you calculate the radius of an atom. If you want to see how this is derived, by all means, be my guest. Have a look at some videos that are going to show you how those are derived. That is how you, in this slide, this is how you are going to calculate the radius of the atom through the size of the unit cell. Yep. But next one is how to calculate, how to use the density to calculate a few properties of your particles. Now, obviously, the density of a metal with a body-centered cubic structure is generally less than that of metal with either hexagonal, close-packed, or face-centered. Yep, obviously. How do we know that? It's from here. And you can see body-centered has only two particles per unit cell, whereas your face-centered has 4 particles per unit cell, and hexagonal here has 6 particles per unit cell. That is why the density of your body-centered cubic structure is less than that of hexagonal or face-centered cubic structure. This is because the atoms in hexagonal close pack and face-centered cubic, they are arranged in the closest possible way, and they occupy 74% of the surface in the lattice. The other remaining 26% is void, is empty space. But 74% of the space in HCP and FCC is occupied um, by atoms or by particles. On the other hand, atoms in body-centered cubic, they are not arranged as tightly as in the HCP and FCC. And obviously in body-centered cubic, it is going to only have 68% of the space occupied by particles, less than your HCP, FCC. These are the close packed. This is not the close packed. Yeah? The close pack is HCP and FCC, whereas the BCC is not an example of a close packed structure. And how are you going to calculate the density through the edge of the cell? Now, everybody knows that density is mass over volume. Betul? So density, which is we're going to calculate usually in the unit of gram per centimeter cubed, is mass over volume. So when you are doing your calculation, remember to change all your length into centimeter and all your masses into gram. So it's easy that way. So obviously molar mass is equal to mass over mole, correct? Relative big M is relative molecular mass is equal to the mass of that particular element divided by the mole. So the mass is molar mass times mole, and mole is actually the number of atom divided by Avogadro's number. This is all very basic. So mass is equal to the relative molar mass times the number of atom divided by Avogadro's number. So you can rearrange to have mass is equal to N times molar mass. N is number of particles or number of atoms. M is the molar mass divided by Avogadro's number, and you plug that up, put it in here. Mass is N times molar mass, number of atoms times molar mass divided by Avogadro's number, and volume is simply A cubed. A times A times A is A cubed, so divided by that volume. So this is the formula that you are going to remember in many calculations that you will face in this topic. And remember, your units for length is always centimeter. If you're given picometers or you're given meters or you're given angstrom, you have to convert that into centimeter to fit into this equation. Yeah. So remember, that's the formula. Rho, which is density, is equal to the number of atoms times the molar mass divided by Avogadro's number and volume. Yep. So I'm going to have a practice exercise for you. Yep. This is a practice exercise where you are given a small bar of an unknown metal X. So you don't know what is that metal. The density of the metal is 10.5 gram per centimeter cubed. An X-ray diffraction experiment measures the edge of the face-centered cubic unit cell to be 4.09 angstrom. 1 angstrom is 10 to the power of minus 10 meter. So from this information, you are required to identify what is X. So how are you going to go around doing that calculation? So it's really quite simple. Remember what is the information that you're given? You are given that uh, this metal X has a face-centered cubic unit cell. This is the structure of a face-centered cubic unit cell with the edge length of 4.09 angstrom. And you remember from the calculation that face-centered cubic unit cell has 4 particles. Remember, in one unit cell, there are 4 particles for FCC, and the edge length is 4.09 angstrom. So how are you going to use this information to determine what is X? So this is it. Yep. So a face-centered cubic unit cell has 4 atoms as determined in here. So for a unit cell, mass of X, yeah, the mass of X is equal to volume times density. So you will be able to find what the volume is, because volume is simply 4.09 angstrom times 4.09 angstrom times 4 times 0.9 angstrom. So it's A cubed. And density is given here, 10.5. So you simply have to calculate the mass of your unknown metal X. So the mass is, if you count that, 4.09 times 10 to the power minus 8. Why minus 8? Because 1 angstrom is 10 to the power minus 10 meter. And then if you convert meter into centimeter, you're going to have to go back by 2 decimal points. So it is 4 times 10 to the power of minus 8. Yeah, centimeter cubed times the density. So the mass of X, the mass of your metal X in that unit cell is 7.18 times 10 to the power of minus 22 grams. Tiny, weeny, teeny. Sangat, sangat kecil. Now, what will you use this information to? You're going to say mole of X is equal to 4 divided by Avogadro's number. Yeah. So 4 atoms divided by Avogadro's number is 6.642 times 10 to the power minus 4 mole of X. So 7.18 times 10 minus 22 gram of X is equal to 6.62642 times 10 minus 24 mole. So senang saja. Molar mass is equal to the gram per mole. So you just divide your gram with your mole. You are going to have 108 gram per mole. Go to your periodic table. What metal has a atomic molar mass? The molar mass of 108. Go to your periodic table. You're going to find that it is silver. Yeah, it is silver. So that is how you're going to find information like this that you can manipulate how to determine the type of metal that you have. Is that all right? Are you okay? So I hope you are okay with that, because I'm going to give you one more practice exercise. So platinum, now this one you don't have to determine what is the metal. Now you are given the metal. Platinum crystallizes in FCC lattice with all atoms at the lattice points. It has a density of 21.45 gram per centimeter cubed. You are requested to draw the unit cell of platinum, FCC. Obviously, you're going to be able to draw it very fast. And then you are going to be you're required to calculate the unit cell age length of platinum. And then from there, you are going to be asked to calculate the radius of a platinum atom. So please try this practice exercise number 2. Use this as a guide and use this information in here. FCC, so A is equal to square root of 8R. Use those information to get yourself 5 marks for practice exercise number 2, right? So next, we are done with metal crystals. I'm going to stop here because this is already 50 minutes of the lecture. So my lecture 10 is going to stop at this practice exercise number 2. So I'm going to continue on lecture number 11 to go into the next topic, which is ionic radii and ionic crystal structures. With that, I bid you goodbye. Be safe, keep healthy, keep happy, and go on studying. Inshallah, you will be fine. Take care, everyone. Okay, assalamu alaikum.